Okay, hello everyone. Sorry I'm late. I had to deal with a case of fraud. All right, so let's go over this week's module before I start. So this week we are going to work on robot control. So on Friday when I talked about joint control, I think when I looked at the class, we had half a class confused, probably because they never dealt with control before. So I designed today's class to be a review. So I sent an announcement if you have had control before, you don't have to attend the class. You can just do the class assignment. If you're here, say you're bored, you can leave. Otherwise, it's a good review to just touch up and freshen yourself with the concepts. And then Wednesday and Friday we'll jump into control. We jump back where we left off. All right. I released homework 4. So homework 4 individual, if you look at coding on MATLAB, both of the questions. Question 1 is simple, trying to getting you more familiar, or if you have never worked with OD45, to go find it on MATLAB website, become familiar, solve a simple problem with it. Question 2, you have to use OD45 plus, you have a system of equation you need to solve. This assignment is designed based on the prerequisites of the class. All right, take a look to see if you know how to do it. Don't wait for last minute. If there is something you don't know, for example, if you don't know what's the change of variable method, then either you need to tell me, I'll post something, or you have to go and find it. It's not too difficult, all right? But take a look. If you know what to do, then you can do it for last minute. It shouldn't take long if you know how to use them. If you don't, then you need to learn. All right, so it is based on the prerequisite of the class. So this is kind of telling me what's the level of the class, because some of us don't remember the prerequisites very well. All right, that impacts the learning experience. So supposed to be challenging for those of you that never worked. All right, get ready for spending a little bit extra time on that. Today's class participation, we'll go over, we'll do it in class in a few minutes. I posted CP 18 solution. I realized I forgot to do that, but it wasn't related to exam, so I think that's why I postponed it. Exam 2 solution is there. I brought the exam papers. Grab your papers, make sure the numbers that I put for question is the same number that I put in the rubric. All right, because I just did all of them this morning. I might have made a mistake in just entering the numbers, right? Make sure the numbers matches the numbers on the rubric. And if you have any question on the grade, you can talk to me, probably not after the class, maybe in office hours. I posted the solution so you can check actually how you have done, how you did. And I tried to grade leniently, like very lenient. Still the average was not very high, but it's okay. Any other question? Any question so far? Anything? All good? All right. Let's go now to the lecture. Also, my pen might die. All right, last class we discussed, wait, it's not working. All right. Last class we discussed block diagram of a robot manipulator using a controller, right? So where the controller is. So now this is a kind of a review reminder of what happened last class, just the block diagram, because we're going back into control. So a typical robot system, it could be an autonomous vehicle, it could be a quadcopter, a system that you want to control, right? You will have a desired behavior, desired input. It could be anything that you desire. You can control the force, velocity, position, right? Anything that is desired to be controlled, that's going to be your input, right? So you have to find the input to your system that will result in controlling that behavior. Then you will have your controller, gives you low power control, so a signal that you usually have to amplify to go to your system. Then between your actuator transmission because we're gonna have here, it's gonna be a car, just a robot join, any system. There will be another local feedback between them. Did you send me the signal I needed to receive? Just make sure, and then goes out of that, and then the output of that goes to your system environment, the environment. So example we saw was very simple. Usually robot, you have noise from environment, right? So they're all going to be part of your system, part of the environment. So when we model completely a system, you see all of that in that block. So that block has sub blocks in it. So we're just putting a box. This is my plan with everything in it. This is going to be my controller with everything in it. I'm going to have some amplifier in between, some actuation, control. Then here you have the output. So let's say this is output. This was your input, right? In actual system, you will read your output through a sensor, right? Let's say you have encoder on your servo or your DC motor. You believe you moved 5 degrees. You check the encoder tells you how much you actually moved, right? Now this is depending on what you read from the sensor, the resolution of the sensor. You might actually move 4.5 degrees, but the resolution only shows every half degree, so it might show you 4. That's the best measurement you can get. But your model will tell you you actually move 5, right? So there's going to be a difference between these two. So your system depends on your actual measurement, depends on the resolution of your sensor. So you read that and you go and compare that with your reference input. Is that what I wanted? Yes. Okay, just don't change anything. Keep going in time, something might happen, and I need to readjust my controller. It's not the same. There is a difference. Okay, let's adjust things. The simple example, cruise control your car, right? So now think about that. That's going to be your task participation. So you're going to draw the block diagram of cruise control. But think about, I want you to identify what the input is, right? So from human, so you're the outside system, right? You're going to insert the input. What's the input applied by you? Then what happens in the controller part? Then what is your system? What's the output? How do you measure the actual velocity, speed of the car, right? And then say, let's say I wanted to go 45 miles per hour, right? You do something to go to 45. Goes to your controller, goes to your system. So at the beginning, it just goes to your system. You read out, it's 30. You have a sensor that reads that value. 30, I want it to be 45. There's 15 miles per hour difference to continue the change, right? Until I'm 45, I want it to be 45. So the car is 45, something in the car, right? Might not be accurate, but that's all you have. 45, okay, good. Don't change anything. So your controller doesn't change anything by time. Then you are climbing a hill, right? Going up the hill, and then speed drops because you have extra forces, right? Then instead of 45, now you're 43. The cruise control says, hey, you drop in 2, and then you hear the motor will act, something happens, and then you go back to 45. You're going on a straight line, and then you're hitting a bump. Something happens, you might not have that 45. So the controller makes sure that during the time of operation, you're always at your desired value. So there are noises and inputs, forces from the environment that impact the behavior, right? Does that make sense? So now to kind of getting ready, preparing yourself for control, I want you to draw the block diagram for cruise controller, things I need to see. What do you think is the input? What is the output? And identify all the blocks. Don't worry about if you have seen all the blocks, think about the main ones, what it should exist in my car. All right? So go to CP19. I'll give you 5 minutes, 8 minutes. 5 should be enough. 8 minutes. Do not rush. Don't look online for block diagram of cruise control. This practice is for you to prep yourself for what's coming. All right. I will grade you based on completion. So do not look online. You can put it here. You can. Yes. So you have input, you have the system, and then you just simulate and find what the output is. That's the second type of problem. The third type of problem is I have a system, I have a desired output. I want to know what input can give me that output. Then I can control the input to always get the desired value for my output for system behavior, right? That's control problem. Now the thing is, sometimes to solve control problem, you have to solve the other two. Because you don't know what your system, you bought a robot, you have a robot, you have to model that, right? So you assume an input, there's an output for the system, so you model. Then for every input, you have the model, you get the output. That you're trying to make sure that your model works. Because you probably linearize a lot of things. You want to make it close enough. Once you got that, then you solve the control problem. Now, when we're saying solving control problem, you usually ask yourself one of these questions. Then you know you have a control problem. You say, how can I get my system to meet my performance requirement? Or how can I automate my system? When you're automating something, you have to make sure your input always gets you the output you want, right? So you can leave it on automation. So when you ask yourself these kind of questions, you have control problem. It's a good problem, in my opinion. Now, there is a definition. I don't know if you've heard or not, but what's the point of all of that? Okay, I know I have a control problem, but what is the outcome of this? Like, what am I getting after solving my control problem? You're getting control law. So you're developing a law for your input that whenever you plug in your input, you're sure that you're always getting the desired output. The control law, we're talking about this a lot. Basically tells you so it changes the input over time to achieve desired output. So simple block diagram of any system with a feedback control. Reference, controller, plant, output, sensor. You see that the input to your plant might be different from the reference. Reference is something you want to track. The input to your plant is something your plant will understand. Right? So if it's a voltage, it might be a force. So that's different from your reference. Now, I see that some of you, whenever I ask design and control, you put PID right in there, right? PID is one of the solutions. This controller has to make sure, control law, that over time, you're always achieving that desired output. Sometimes PID control is not the answer. because once you tune PID coefficient, you leave it there. You don't touch it, right? Other control you can design such way that over time they will change. You can use methods such as scheduling to change the value of PID over time. Do some calculation and update those values. You can have observer in your system to make sure that your states are always defined properly. There are LQR, sliding mode control. There are so many different ways of controlling something. PID is desirable because the control law is simple. You can grab it anywhere online. All you have to do is calculate your error, which comes from your system, always output minus input, right? The upfront work is to tune PID, which is a little bit of work because it's mostly trial and error. Other controllers, defining the control law is harder, but once you have it, you do. All right. So choosing PID is one step of the control problem. So don't always go with the PID default that my controller has to be great. Right? There are different compensator and controllers. Now, so these are all basic and fundamental information, but I expect you now that you've heard it, you know that. Open loop versus control, open loop control versus closed loop, or open loop system versus closed loop. Both of these are similar systems. The only difference is one is open, one is closed. So when you say open, we get our desired speed. So you see that here you have a desired speed, but here you have a battery that you can adjust the voltage, right? And then you will reach to, for a specific voltage, you will get to specific velocity, for example. You have amplifier, DC motor, that's rotating this. So that's our system. This is the block diagram. You have an actual speed. All right. You see that you don't read the output and don't send it to the input. This is an open loop system. So the loop never closes. Why do we use open loop system? Should we use open loop system? Are they useful? Think about open loop systems around you. Have you seen pretty lawn in front of the houses here? And there's this water sprinkle, right? How do they work? It's a system. There should be a controller. How do they work? Timer. You set a timer, but you don't check if all places, all the soil get the same amount of moisture. You accept. I'm going to run this for half an hour, whatever happens, right? Your dryer, if it's not super smart, it doesn't have a drying sensor. You set the load. Okay, this is normal load. Okay, it probably measures the weight and say, okay, 59 minutes. Then after 59, you open, my towel is too wet, right? It doesn't check, you have to run again. Use a timer. So if you only have a timer, no sensor to check, that's an open loop. But usually maybe it's fine. You don't have to, because having the open loop, extra cost, extra money, extra power, maybe doesn't worth it. Your toaster, bread, you put, and then for number 4, so it's 7 minutes, 2 minutes, 3 minutes, run, finish, you check, it's not brown enough, you put it back. So you are actually the feedback, right? But you're not in that system, you're extra feedback. Now those are your open loop systems. Sometimes the system only needs to have open loop. You don't care. You accept the result. Sometimes to read the exact values are important. You are going to the speed limit. You don't want to get a ticket. You put on 79, so you're only with 100. So you're using all state app. So you can get some discount back. You're always 79, right? It's important. So that has to have a feedback. So if it was in this system, you have a DC amplifier, DC motor, that's okay. That's my view probably. I'm going to have a tachometer, so I'm going to see how much I'm actually, what's my speed, right? Let's say that all the aerodynamic of the car has been seen in this model. So I'm actually going to go 79. So the cost is 79. And then goes there. Now you have a closed loop system. because the feedback is important, right? So that's the difference between your open loop and closed loop system. So you don't always have to have a closed loop system to have a controller. You could have a controller, right, by an open loop system. It could be simple P control, just a gain. Amplify my input by this much 10 times and feed it to my system, I'm good to go. I don't care. I'm sure that it will satisfy my needs. Make sense? So you don't have to have feedback to have a controller in your system. All right. Other thing, so I'm introducing this massive spring damper system because I want to talk about the system response in time. This is the simplest system, and most of us probably are familiar with. So think about a spring, and you have a mass, and then if you pull a little bit, what's going to happen? Right? So up and down. If it is in this direction, it will reach to some. It will stop eventually, right? Because of the gravity pull. But if it was on the surface, depending on the friction, it might never stop, right? So use the, so here I use Newton's second law of motion to get the equation of motion. Dynamic, we already know this. Equation of motion, so you could have translational forces and torques and rotational. I'm hoping that you're all familiar with this. If not, it's not a big deal. You're not gonna, you're just basically gonna see how this behaves. The response is when, so let's say it was on the floor, so it's gonna go back and forth. So let's say that I put a force F here. And let's say this F changes with time. It's not constant. Or it could be just a constant, like you hit it with a mallet or something. All right, starts the motion. If you measure the position of one corner and always look at that and draw in time, so if this was position, it was time, you'll see that sine wave kind of motion until it reaches to some point and does not change. When it reaches that state, what we call that state? Steady state, right? So now, if this was a control problem, our steady state could be your desired position, right? I have a desired position. How do I change my input to reach that steady state? And you see that it takes a little bit of time for your system to get there, right? The time that for your system to get there is called transient time. So you're transitioning from the beginning of your motion to where you reach a steady state. After that, steady state, because you're not changing anymore. Right? So second order response. The response could change though. It could have underdamped or critical damped, but we're looking at the well, worst case scenario. Not worst case scenario, but what you usually see. So what you have a different one, right? Correct? Yes, this is wrong. What you have is right. And the wrong is here. I said it's the same error, but it could YSS. So follow what you have. I'm gonna write down. So this is system response for any second order system. All right. I'm going to define a few values. You might have seen them. If not, you're going to use these values on Wednesday and Friday. So you can always also Google second order time domain response, and you'll find all of this. Things that are important. One is Y of final value, wherever your system ends up. You can also call it YSS, steady state value. So this is your final value of steady state value. Sometimes your system might not have final value. It might oscillate like that, right? But it will be bounded. Then we have MP, which is the maximum overshoot, you will find it from your Y max minus your Y steady state or Y final value. So you see MP, the difference between Y max and Y steady state. So this is the step response to your system, meaning that the input looked like this. At time 0, the input was 1. We expect our system to track that, but you'll see that the system is showing something like this. So this part is our transient. It takes our system a little while to track our input to finally have the same value of 1. So using a step input is one of the ways to check your system if your controller is performing well. All right. MP, then you have a percent overshoot, which is 100 e to the power of negative pi zeta square root of 1 minus zeta squared. Do you know what zeta is? Damping ratio. I put that in your annotated lecture. All right. Then we have peak time, TP, which is going to be pi over omega n square root of 1 minus 2 zeta squared. Do you know what omega n is? Natural frequency, right? Then we have TR, rise time. So TP is peak time. When does my system reaches its peak value? T rise time is the value between 1% of YSS to 90%, 10% of YSS to 90%. How long it takes to fill that? So what do you want? So for a controller you design, what do you expect this TR be? Is it the smaller TR better or larger TR? Smaller, what does it mean? Got there faster, right? Now think about, now sometimes when this is faster, you might have a bigger overshoot. So absolutely small value of PR doesn't mean it's a good controller. So it's a trade-off. So all of these values, you want to find them and then find the best optimized behavior for a controller. Sometimes you will get a specific value. Make sure your rise time is below this second, or make sure that TS, the settling time when you reach the 2% of your final value is below this. So this TS, we want it to be shorter. We want to get to our final value faster, right? But if this coming toward the left makes a very large overshoot or loss of oscillation, you might break our motor, for example, because it's jerking back and forth, right? So designing a controller, basically looking the behavior of the system, it's a little bit of trial and error to make sure by changing the controller, how does your system perform? So this plot becomes really important when you are looking at the system performance or behavior. Now, this is something that we're going to work on, and you will see on Wednesday, there will be quiz about this. The quiz will be slightly different from this, but this solving this should help you to be able to do the quiz on Wednesday. So you have an open loop system. You have a reference of R. You have a controller that has a gain of 110, just a gain. You'll see later that this is a P controller, just has a proportional value. Now you have U input to your plant. Then you have Y, which is your output, but you also have a noise coming to your plant and going through a gain. So that part is what we design. You say, oh, that's the kind of environmental noise I see. I can model it as a noise always going to the block with this gain. Now you have different way of designing noise, right? And we will model that noise based on our environment, all right? Now, we want to find the control loop error. Control loop error here is input minus output. I'm breaking in the steps so it's easier to do. First thing I want to know is what is this U? So I want to know what is the signal going into my plant. U is R, this signal value times the gain. So this is R over 10. Now, from the plan, YOL is, I have W signal times 0.5. So this is 0.5 W going to this summation with negative. U goes in here with positive sign. So U minus 0.5. So this is U minus 0.5 W going into a block with gain 10. And I know that from previously U was R over 10. So R over 10 minus 1/2 W times 10, which is R minus 5 W. So this is YO. So I calculated YO from my plan. Now, what's the error? Input minus output. Input R minus 5 W, R minus R plus 5 W. So error is going to be 5 W. This cancels out. So see that the error in the system depends on the noise. If you design a controller, you want to get rid of that noise, right? So you come up with a controller that will get rid of that noise. Make sense? Yes, that's what you're thinking about? Exactly. Now, if this was a closed loop system, all you have to do when you're calculating, find out what are the values that goes through the signals, goes to the summation point, then find input minus output for your control, your error. Question? What? Your desired value minus your actual value. So here we don't have any feedback, right? So our actual is the output here, Y over L is the Y. All right, so this is basically explaining the error dynamics. So kind of jumping back into robotic, what we discussed before. So if you have a joint and you have a desired theta for it, right? You want to find out how much error you have. You say, okay, this is my desired theta. I'm measuring the theta, which if you're using a motor, you probably have an encoder, right? So the actual value is what you read from encoder, or if you don't have, you already model. You're gonna model and see what's the output from that model. So the desired minus your actual is going to be your error. Now, desirably, we want the error to be 0. So we will write the controllers in a way that error will go to 0. So that will be the purpose of designing any controller. So we looked at the system response, right? Now, when we are designing controller, we are actually going to look at the error response. So what do you expect the error response to be based on what you saw from the system response? The system, you started from 0 for a value. The system shoot up and then came down and back to your desired value, right? Which is 1, for example, for a step. So what do you expect to see if you plotted the error response? Let's say you have a non-zero error at the beginning, Michael. They will fluctuate with time. Okay, Cam, did you wanna? So between the both of you, so when you have a non-zero error, so you start from a value, right? That's not zero. The goal is to go to 0. So you're going to drop, maybe overshoot a little bit, go back up, the controller is behaving, right? And then until you get to 0. So kind of the flip. So if you mirror your error, if your error mirrored your time response, just the way it looks. So you're starting from non-zero value and your goal is to get to 0. You will usually have this overshoot. Now it looks like it's undershoot, but it's not because it's the beginning of your system. Now the goal is to reach from this point really quickly to this. So that's the controller that you desire, right? But sometimes getting something like this is very expensive. Time, usually time and cost. You need a very strong motor, for example, to get there. So sometimes a controller that looks like this might actually not to be a bad thing if it costs you $100 instead of $500 per month, right? So understanding of how my error response should look like is really important. That will help you to design an optimal controller. Let's say you're using PID because it's the easiest to design. All right. Again, you're doing this to understand what our system will behave. I haven't talked about any controllers yet, right? All systems behave like this. All controllers behave like this. So to just finish up, this is the part. So after you reach, so we usually say that if you reach the 2% settling time, you're done. So this part is your steady state. And this part is your transient, things that happen in transient. All right. So when we discuss our PID controller on Wednesday, you'll see this show up again. And use this plot to find a specific characteristic of our system. All right. Any questions on this review lecture? All right, awesome. You're all great.